Now, to start off with, I've got a simple problem for those of you who can handle it, and it's very simple. We had an engineers got together and they wanted to put a cable all the way around the earth. So they were in the process of doing this, and then they realized the cable, if it's laying on the ground, it's going to rust. So their solution was little 1-inch blocks all the way around the world to take the cable off of the surface of the earth so it wouldn't rust. The problem is, how big a piece did they have to add in when they got through? They had to make the cable bigger because it's going around all these little blocks. Now, you have enough data to solve that problem. You probably think you don't. You don't need to know the diameter of the earth or anything like that. You just need to know the old formula that you've all been taught, that circumference equals 2 pi r, or pi times the diameter. 2r is the diameter, 2 times the radius. So if you look at the equation, you can also substitute that to say the change in circumference equals pi times the change in the diameter. And you know the change in the diameter, if we put 1-inch blocks around, the diameter increased by 2 inches. So the answer is simple. It's 2 pi. It's a little over 6 inches. Pi is 3.14, so it's a little over 6 inches. Interesting subject is fluids. Now at high velocities, fluids act as solids. Now you can tell this if you, next time you're in the pool or in the water, slap the water with your hand. You're hitting it at high velocity and it feels hard. If you would drop from an airplane, it wouldn't make much difference if you landed on the surface of a lake or the surface of the freeway. You would still, at that velocity, it would be the same as hitting a solid. When you skip a rock across the lake, the rock's going at high velocity, it hits the water acts as a solid. When a propeller from a boat goes through the water, it doesn't move the water very much. It just unscrews in the water. If you see underwater photography of a propeller going through the water, it's just unscrewing its way through the water. If you drop a balloon full of water, you might as well drop a bowling ball. I saw a video recently of a huge digger with a bucket full of water, and he dumped it on the car. It just flattened the car. It was the same as if he had dropped a load of bricks on it. So fluids act as solids at high velocities. Remember that. Now you may study this in high school. I didn't until I got to college, but they're teaching things in high school now that I took in college. Optics, very interesting. Magnifying mirrors, concave, convex mirrors. A lot of convex mirrors are used on cars today to see a wider range of field. Concave mirrors are used as magnifying mirrors, and then you have all the lenses. But to play with this, find yourself a magnifying glass, large one, and focus it at you and slowly back up. If you back up far enough, your image will flip and you'll be upside down. And then when you get into studying optics, you can understand why. It's not really complicated and quite interesting. Now, resonance, vibration and resonance is another interesting topic, I guess. From the way I'm using the word interesting, everything's interesting. But everything has a natural frequency. Your body, this scale, this little ruler, everything has a natural frequency. A bridge, an engine block, everything. Now the pendulum on a clock has a natural frequency. Anything. Now you can change the natural frequency by two things. You can increase the mass, that'll slow it down, lower the natural frequency, or you can decrease the mass, and that will speed things up. The other way, you can make it stiffer. If you make it stiffer, it will increase the natural frequency, raise it. If you make it less stiff, it will reduce the natural frequency, such as the pendulum. This is what makes a clock keep the proper time. If you shorten it, make it stiffer, it swings faster. So the way you regulate a clock is simple. You take the mass of the pendulum and raise it to make it run faster, or you lower it to make it run slower until you get it exactly where you want it, and you just leave it there. And the natural frequency of that system is compatible with the clock, and you keep perfect time. In the case of a steering column, we're always worried about steering wheel shake. Now, the cars you drive, none of the steering wheels shake, I guarantee you, because they've been properly engineered. But a steering column is mounted at the toe board, and then it's mounted at the lower reinforcement of the instrument panel, and then a rather heavy steering wheel and horn mechanism, and now airbag, sits out here, cantilevered out on that column. And you don't want it to go into resonance and start dancing around while you're going down the road and hitting a few bumps. So we do two things. We make the steering wheel, we reduce the mass as much as we can, and we make the column as stiff as we can. We drive the stiffness up and the natural frequency up high enough to where the normal driving inputs will not excite it. It won't put it into resonance. When something shakes at its natural frequency, we call that resonance. Years ago, there was a bridge over the Narrows Valley where it's a suspension bridge that was built, and they thought they had protected against the high winds. What they didn't realize is that the winds were high enough and the natural frequency of the bridge was low enough to where they coincided, and it set the bridge in resonance. And they have films of this with cars falling off and everything. People had time to run off and get off the bridge, I believe. But the thing just tore itself up because it got into resonance and there was nothing to dampen it out. When soldiers years ago used to march wherever they'd go, they would march in cadence, all in step. And if that frequency of their marching matched the natural frequency of a bridge they were crossing, the bridge would go into resonance and collapse. So to prevent any danger there, the armies would break cadence and march randomly so that they wouldn't excite any bridges they would cross. So before they cross a bridge, they would get out of cadence and walk across the bridge. Now, columns are a little different. If you load up a column, it will bend into an arc one way or the other. If you restrain the center of it, you're essentially putting it in, making two columns out of it. And if I can load this up enough, you can see it turns into an S. And if you would take a column long enough, restrain it in three places, it would bend like this and be able to carry quite a bit more. So now on beams, when you load up a beam such that if you put a couple of bricks down, put a board across it, stand on the center of it, it would bend. It might even break. If it breaks, that means the tension at the bottom of the beam, or if the beam was like this, the tension at the bottom was too great for the tensile load of the material, and it breaks. On the top, it's in compression, and it wants to crush itself. So if you have a piece of wood sitting on the bricks, you step on it, the bottom tears apart in tension, the top pushes against itself, but wood's pretty good in compression, and it probably would show no signs of compressive failure. concrete is very good in compression, lousy in tension. If we have a beam, and we support it at the ends, and we load it up here, this is the tension force I mentioned. High tension. This is a compressive force. So when you load it up, this wants to pull apart, this wants to go together. What's interesting, if you measure the tension in this beam, inside it would be a little less tension, and by the time you get to the middle, there's no compression or tension. And the same thing goes for the compressive forces. So the tension and compression reduce to the point where it's zero at the center. So now, knowing this, the engineers years ago decided, if that's the case, let's put all of the strength, the strong material at this end, at this side of the beam, to withstand the high tensile forces. Let's put a gutsy part of the beam here to withstand the compressive forces, and then we just need a web to connect the two. So what they did, they took a piece of steel there, piece of steel on the bottom with a lot of guts to it, and then connected it with a web that all it had to do was keep the two pieces together, and they discovered the I-beam. So now all your bridges are built with I-beams. Any structural thing is built with an I-beam. All of the compressive loads are here, all of the tension loads are here, and this thing just goes along for the ride.